we have Jochen from DLR Germany. Jochen is a researcher in theoretical quantum optics as well as quantum information, and he is here from DLR. It's a pleasure to have you, Jochen, please.
All right, so we've already heard quite a bit about quantum computing, about how to do it, what materials to do it with, what it can do, what it can't do. Thankfully, we've also heard a bit about that. But I wanted to speak a little bit more about how to use it. That is, how to bring quantum computing to the masses, should that ever become interesting. So my topic is mainly facilitating quantum readiness. So just to give a quick reminder of the motivation of why we think quantum computing could be something interesting. So there's an intuition pump that I like to start with, which is that the basic observation is that quantum systems are really, really complex things. They have typically scaling with the number of constituents that is exponential, and so that makes them very, very hard to simulate with a classical device. But of course, in some sense, nature does it, right? So maybe we can use this sort of power that is locked inside a quantum system and use it to do some actual effective calculations. And as it turns out, yes, we can do this. So there are certain problems with a certain structure for which we know that quantum mechanics, quantum mechanical systems grant us a speed up in computing them. And well, by piggybacking on the natural complexity of quantum systems, we can make use of this computational power and accelerate certain applications. So this sort of engenders three natural questions. One is, so what sort of problems can we actually accelerate in this way? The other is, well, okay, now if we know that, how do we do it concretely? So how do we implement the quantum computer in a concrete physical system? And once we've done that, the next problem is, how do we actually get people to use quantum computing for their use cases? And I think this sort of harkens back to a point that Oliver made in the morning, or I think it was the first of his controversial thesis, that in the future the software will actually drive the hardware development. And in a sense, this means because, well, what drives the software? Well, the use cases drive the software, right? If there's nobody who's interested in doing something, nobody's going to write software for it. And if software drives the hardware, then nobody's going to build the hardware. So we need to think about what use cases we actually have that permit of a quantum speedup to get the development of the requisite applications and then to actually implement the most promising quantum computer architecture that fits best with these ideas. So at the DLR, we have set us the task of identifying our valuable use cases. So our cases were the domain experience, so the domain experts are going to meet the quantum experience. So even in a large and diverse research landscape like is present at the DLR, there are many people who are very, very familiar with their own areas of research, but who might not be too familiar with the field of quantum computing. It's just understandable because it's still relatively new and not something that everybody learns about in grade school maybe. So the challenge is how to actually get those people to realize that, well, maybe I have the perfect use case for quantum computing sitting in my research area. So there's this problem I can't do classically, and there's actually a way to do it with a quantum computer. So once we have this in hand, we can basically, once the requisite technology becomes available, just take off, implement it, and then possibly get a huge advantage over the competition. Right, so this is where the project Elevate is located. And by the way, as regards this sort of only weakly indicated acronym. Don't bother much with it. So the running joke at the DLR is that we already need the quantum computer to actually compute our acronyms from the actual project names. And yeah, so the large-scale goals of the project are to enable our institutes to assess quantum advantage of their use cases, to identify the most promising applications, and to develop a quantum computing application landscape at the DLR in order to basically become as quantum ready as possible without having the actual devices under every desk. And exactly, so the basic structure of the project is bipartite. That is, there is an enablement and an experience track, and in the enablement track we are looking to sort of educate our user base in the ways of quantum computing, which we are happy to have already done for about 150 of our users. So there is a large amount of interest present, and we are seeking to enable them to assess the quantum advantages of their potential use cases, doing so by various lectures, hackathons, and workshops on the topics of quantum computing, quantum simulation, quantum optimization, and machine learning. And on the other hand, there are the concrete experience studies. So basically, these are mini projects that are distributed on a voucher-based system, which I will talk briefly about shortly. And they are, so basically the institutes, they come to us, or they come to me because I'm the project lead of the Elevate project, and they are saying, hey, we have this potentially interesting use case, and we would like to sort of get funding to investigate this use case, and then there will be an expert round of judging whether the use case is potentially interesting. And for the vouchers that survive this process, then there will be basically a member of the quantum experts paired with the institute to implement and assess and potentially even realize the first test cases for the basic application. So the end goal of this whole process is then to create a roadmap of potential quantum, interesting quantum use cases, so that we can, from this starting point in a sort of hardware-software co-design phase, then actually design quantum computers to order for the basic use cases that we have identified, and then just reap the benefits of the quantum speed up for our research purposes. Right, and so the basic idea of the voucher system is that we want to present an agile sort of landscape, an agile system that allows our institutes to reap their first experiences with quantum computing. So each voucher is basically a sort of mini project, a financed mini study that is carried out in-house, and where each of our institutes has the opportunity to sort of get a funded quantum consulting, so get support for quantum consulting with their use case, and also they will be supported in their own research from this sort of voucher budget, and each voucher then leads to a mini project which is relatively slim administratively and quickly implemented and carried out, and is focused on content and on results, and is supposed to basically just give each institute which has an interest a slim opportunity or quick opportunity to assess their own possible quantum advantages. And in the end, as we hope, we will have a quantum roadmap that will tell us where and which resources we have to reap benefits of quantum computation at the DLR. All right, so this is sort of the intended result of this in-house project, which is kind of intended as a roadmap to, well, everybody has heard about the digital transformation. I'm not going to use the word quantum transformation, but at some point we are going to have to talk about how to actually make our customers, our own firms, whoever, quantum ready. So this is sort of a potential roadmap to that end. But of course, the DLR is not only focused on its own in-house concerns, but also takes part in the wider industry landscape for quantum computing in Germany and in the EU. And this is the domain of the DLR Quantencomputing-Initiative, which is financed from the Federal Ministry of Economics and Climate Action, and has received a funding of 740 million euros, with 80% being intended to go towards industry, towards startups, and 20% to the research and development at the DLR. And the aim is, in a certain sense, similar to the Elevate project, just on the larger scale, that is to identify, to realize, and to pair the quantum expertise with the industry know-how for the use cases that are supposed to be realized. And this is currently leads also to the building up of 2 quantum innovation centers in Hamburg and Ulm, and the development of our own in-house quantum computing systems, where we are currently exploring the various technologies which we have in parts already heard about today, and their use for quantum computing for the different use cases. So right now, the Quantum Computing Initiative is supporting 39 different projects which run the full quantum stack, basically from the hardware-based side of things up to the software and enabling technologies, and then finally to the use cases, again with a view towards back support from the use cases to the hardware. And so as you can see, we are supporting there various of the different technologies, which some of you that have looked at the session in the morning already have heard about, and some of whose collaborators are perhaps even here in the audience. And just to give you a sort of sampling of projects that are happening right now. One is the Toccata project, which is building a scalable quantum processor with 50 or more qubits on the basis of ion trap technology. And on the software side, there is the RKIP project, which introduces reliable quantum information processing, and a project that is basically a use case study is the Quantum Mission Planning Challenges project, which seeks to use quantum optimization strategies to facilitate the planning of complex aerospace missions, which is being developed together with the contractor E.ON. Right. So, and for everybody who is interested in taking this further, there is an open funding call right now from the Federal Ministry of Education and I forget the English word. We are currently looking at finding partners for new consortia, and if there's any interest in this, just contact me across any of the various open channels. Right.